Welcome back, engineering and procurement students. Today we're going to completely demystify the absolute alphabet soup that is international aviation safety regulations and digital procurement. In this explainer, we're taking a pretty wild ride. Starting from the absolute highest macro level, we're talking United Nations treaties, all the way down to the microscopic level of individual parts tracking. If you're gearing up for a career in aerospace engineering, supply chain management, or regulatory compliance, mastering this architecture isn't just a nice-to-have, it's literally an absolute requirement to keep the global fleet safely in the sky.
Okay, let's dive into this. Consider this your professional syllabus for the day. We'll start with the global aviation architect, move on to designing and maintaining safety, look at the national aviation authorities, figure out crossing borders with parts, and wrap up with the digital procurement framework.
All right, Section 1, the global aviation architect. Let's look at building the global regulatory architecture.
So right at the apex of this global safety architecture sits the International Civil Aviation Organization, or ICAO. They were established way back by the 1944 Chicago Convention, and ICAO basically acts as the ultimate architect of global aviation. But here's the absolutely critical thing you need to understand. ICAO is not a direct inspector, right? They don't issue design approvals, they don't sign off on maintenance releases for a single part. Instead, they define the baseline blueprints. These are the standards and recommended practices that member states have to adopt. Now, this framework has evolved remarkably, from those post-World War II treaties to the insanely complex digital supply chains we use today. And just to prove these are living engineering documents, get this. By November 2026, these standards are going to explicitly encompass remotely piloted aircraft systems. That means tomorrow's unmanned drones are going to be subject to the exact same rigorous supply chain rules as today's commercial jets. Wild, right?
Now, the crucial mechanism that actually makes all of this work is called mutual recognition. You'll find this defined in Article 33 of the Chicago Convention. Without this specific legal mechanism, honestly, the entire international air transport system would just instantly collapse under a massive tangled web of conflicting national standards. Basically, it dictates that as long as a state meets or exceeds ICAO's minimum standards, well, other states legally have to recognize their airworthiness certificates. It's literally the legal glue that lets a globally manufactured aircraft fly anywhere in the world.
Moving right along to Section 2, designing and maintaining safety. Let's break down the jurisdictional split of ICAO annexes.
Now, what's really interesting about this slide is the strict jurisdictional split between where a part is actually built and where it ends up operating. Remember those high-level treaty obligations we just talked about? Well, they're put into action through specific engineering and maintenance annexes. On the left, we've got Annex 8, which is governed by the state of manufacture. They completely own the design and production phase, making sure that primary manufacturers have strict quality systems tracing every single part back to its approved design data. But on the right, we have Annex 6, governed by the state of Registry. Once that aircraft actually takes to the sky, the state of Registry takes over. They handle the daily continuing airworthiness, the technical logbooks, and all those formal maintenance releases.
And you know, this jurisdictional split becomes intensely real when we start dealing with harvested parts. Imagine an aircraft is withdrawn from service, just sitting in storage without a proper preservation program. Under Annex 6, you can't just go out, unbolt a part, and slap it onto a flying plane. No way. The airworthiness is completely compromised. So to manage this, ICAO publishes Document 9760, the Airworthiness Manual. It gives national authorities the exact blueprints to issue export certificates and to audit approved maintenance organizations, or AMOs. If an unpreserved part tries to sneak into a new state of registry, these Document 9760 guidelines kick in to ensure it undergoes incredibly strict AMO testing and recertification. It's basically an ironclad wall preventing anyone from bypassing airworthiness controls, keeping the active global fleet structurally safe.
Okay, Section 3, National Aviation Authorities. These are the builders and the inspector.
So while ICAO might write the overarching blueprints, the National Aviation Authorities, the NAAs, they act as the actual builders and inspectors on the ground. They're the ones enforcing the sovereign laws. And here is a crazy statistic. In the massive, multi-billion-dollar world of international component procurement, just 5 key NAAs control the vast majority of the civil aircraft component market. Just 5. As future aerospace procurement officers and engineers, memorizing this exact table is absolutely vital for your day-to-day operations. Seriously, take a good look at the structures here. You've got the FAA in the U.S. operating under Title 14 of the Code of Federal Regulations, and they use the 8133 release form.
Over in the European Union, there's ESA using the ESA Form 1. Then we have Transport Canada with their TCA Form 1, Brazil's ANAC using the Form F100-01, and finally, the UK CAA post-Brexit issuing their very own UK CAA Form 1. You'll probably notice a pretty distinct pattern in the codes here, right? Virtually all of them split their rulebooks into a Part 21 equivalent for design and production and a Part 145 equivalent for maintenance. Knowing exactly which form matches which code, that is literally the foundation of global parts procurement.
Let's transition to Section 4, Crossing Borders with Parts, utilizing bilateral aviation safety agreements.
I want to pose a really practical engineering puzzle to you all. How does an American-maintained part legally fly on a European-registered plane? Because think about it, individually auditing every single foreign repair station would cause absolute commercial gridlock. So to prevent that, regulatory authorities use bilateral aviation safety agreements, or BASAs, to streamline things. And this introduces a massive concept in our field, the mandatory dual release. Let's walk through the exact bureaucratic sequence an engineer has to follow to prevent a huge receiving inspection infraction, which, by the way, would result in the quarantine of a heavily expensive part. Step 1. The US-based repair station actually has to hold concurrent approvals from both the FAA and ESA. Step 2. When they're filling out that FAA Form 81333, the certifying technician must physically tick two specific boxes in Block 14A, one for the FAA return to service and one for other regulations. And finally, Step 3. The tech has to populate Block 12 of that same form with a highly specific mandatory conformity statement. And this brilliantly illustrates the absolute precision required in our industry. This is the exact verbiage that has to go into Block 12. Let me read it for you. Certifies that the work specified in Block 1112 was carried out in accordance with ESA Part 145, and, in respect to that work, the component is considered ready for release to service under ESA Part 145 approval number, and then you insert the number. Now, a failure to populate these blocks correctly, or honestly missing even a single word of this ESA-specific verbiage, the importing maintenance organization must legally reject and quarantine that part. There is absolutely zero room for error here, folks. Finally, we've made it to Section 5, the Digital Procurement Framework, where we'll look at ATA Spec 2000 and commercial standards. So we've talked extensively about the legal requirements, right? But the actual day-to-day logistics? Those are managed by industry associations like IATA and Airlines for America. They standardize data exchange across the whole aerospace supply chain using an international e-business standard known as ATA Spec 2000. It's broken down into some very specific operational chapters. Chapter 1 handles your basic provisioning from manufacturers to airlines. Chapter 2 is all about managing centralized procurement planning. Then, when you dive into Chapters 3, 4, and 6, you're governing material management using advanced XML Gen 2 schemas for stuff like electronic invoicing and shipping. And Chapter 16? That one standardizes the digital exchange templates for those exact airworthiness forms we just learned about, like the ESA Form 1 and the FAA Form 8130-3. But honestly, perhaps the most exciting part for you as tomorrow's engineers is Chapter 9. Chapter 9 mandates that every serialized part carry a permanent, machine-readable 2D data matrix barcode or an embedded radio frequency identification, an RFID tag. This is a total game changer because it means physical paperwork is rapidly becoming a thing of the past. Today, inspectors and technicians can extract a component's entire lifecycle data, its part number, its unique serial number, its manufacturer codes, instantly without doing any physical disassembly whatsoever. It's pretty amazing. Which brings us to the future, and frankly, a huge challenge for all of you. We know from our earlier timeline that remotely piloted aircraft systems are going to fully merge with the commercial supply chain by November 2026. So as drones and unmanned systems begin shipping across borders, demanding dual releases and RFID tracking, will our current web of bilateral agreements and legacy forms actually hold up? Or is the entire digital supply chain going to need a total rewrite? Well, that is the engineering blueprint you will be responsible for drawing. Thank you so much for joining me for this explainer, and I absolutely cannot wait to see the innovations you bring to the global aviation supply chain.